Okay, so good morning. So last time we have discussed the general formalism of solving a one-dimensional, Schrödinger equation for the bounded states. Okay, so we know that suppose you have an arbitrary potential like this one, right? So then we can cut this one into pieces. Okay. Right. So the wave function can be written as, for example, A0 e to IK0 x plus B0 e IK minus IK0 x for x less than x0, and A1 e to IK1 x plus B1 e to minus IK1 x for x less than x1 and then greater than 0, right? And so on and so forth. Okay, so you can have AI e to I Ki x plus B1 e to Bi minus I Ki x. So you can make this into pieces. Right. Suppose the potential goes like this one. Okay. Right, so you can count the number of coefficients. There are 2i plus 2 coefficients. That's important, okay? Right, A0, B0, okay, and AI, BI. So you can use a vector. So you can use a vector, a column, to represent these coefficients. Right. Okay, so these are the coefficients. And then you can have the boundary conditions. Okay. So one is that the psi goes to 0 at the minus infinity. Okay. And then you have x goes to psi goes to 0 at plus infinity. So you should have xi minus 0 equals xi plus 0, the wave function. So this is a continuous, right, condition. Okay. And also you have psi xi minus 0. The first order derivative should also be continuous. Okay. So d over dx psi is continuous. Right. Okay, so this one actually use less than 1, okay, then 2, okay. So let's say 1, 2, 3. They are, yeah. So they are totally 2i plus 2 coefficients and 2i joint points. Okay, for I equals to 1, 2, I. Okay. So you can count the number of equations, right? So now you can count the number of equations. Okay. So number of equations for the boundary conditions is also 2i plus 2. And these equations can be written as a matrix form, okay? Okay. And this one is 2i plus 2 times 2i plus 2 matrix. Okay. Right. So psi is defined right here. So it has 2i coefficients. Okay. And then obviously you can see that psi a equal to 0 if So if this matrix for the boundary condition is not singular, right? So now you can see that to have a singular matrix, you just need to have the determination of this matrix equal to 0, okay? Right? And this one gives us a non-zero solution, okay? Right, so that's the only thing that we can have a solution, right? So this one, of course, gives you, the energy, eigenenergy, right? Which is discrete, okay? Because all the vectors ki are determined by this energy, okay? Right, so this is the equation for the energy. The determination equal to 0 is actually equation of the energy. Then solve this equation will give you us all the eigenvalues, right? So that is why the boundary states are discrete, okay? Because we have these boundary conditions, okay? And now we try to apply this one to the one-dimensional quantum well. Let's consider this one. Okay, so this is V0. This is V0. At this position from minus W/2 to W/2. Okay, make this one to be symmetric. Right. So we know that these wave functions will have symmetric probability distribution. So that means all these eigenstates either be symmetric, like this ground state, but you can also have excited states. That will be anti-symmetrical, right? So this is psi 0, so psi 1, say, and this is psi 2. Okay, this is anti-symmetrical. This is symmetric. Okay, and the energy of this one is E1, and this is E2. This is what we should expect. Okay, and so to simplify the problem, so we actually can write down this wave function in a more symmetrical way. Okay. We can write this wave function into 3 regions. In the first region, we have A1. This is the first region. This is the second region, and this is the third region. Okay. E2 I kappa. Sorry, because it must be a decay function. So we use the imaginary wave vector. Kappa x plus W/2, okay? We counter this one from this point. And then plus B1 E2 minus kappa x plus W/2, right? So this one is for the case that, this one is in the region 2, okay? That means this one is less than minus W/2, okay? And the middle, in the region 2, okay, we write down this into superposition of plane waves. But we can also do this one, and write this one in the superposition of cosine functions and sine functions. So this way we can easily form symmetric and anti-symmetric states. So we do this one, we write this one into Ci cosine K. Okay, X. So this is a symmetrical function. So, but it can also be an anti-symmetrical, C2, sorry, D2, sine Kx. Okay, so that we can automatically have symmetrical and anti-symmetrical functions. Okay, so this is for the region 2, okay? Similarly, we have the region 3. We can write down this as minus kappa x minus w over 2, and then plus B3 e to plus kappa x minus w over 2, okay? And this is for the region x greater than w over 2, so it's in the third region, okay? And to simplify this one, we know that the boundary conditions at the infinite is actually quite easy. So the wave function should go to 0 if you let x go to minus infinity. So that means this one must be 0, okay? So this one should not exist. And similarly, if you let the wave function go to, if the letter position goes to positive infinity, so this one should be 0, right? Otherwise, the wave function will diverge. Okay. So now you have only 1, 2, 3, 4. But this simplification, we have only 4 coefficients. Okay. Of course, we have used the two boundary conditions as the minus infinity and the plus infinity. So there are only 2 joint points right here. So they give us 4 equations. So 4 coefficients, 4 equations. We should have this kind of matrix. Okay. So let me write down this matrix. Okay. In terms of so this one, if you write down the continuous equations, this is kappa 0, 0, and this is kappa minus cosine k w over 2 sine k w over 2, and this is minus cosine k w over 2. This is minus sine k w over 2. Okay, so you can check the boundary conditions at this 2 points. You will obtain this. So these are for the differential. Okay. Okay, so now you have 4 coefficients, A1 and A3 and C2 and D2. Okay, so this one should equal to 0. We call this one M. Okay, and this one is the wave function coefficients, A1. So that has 4 components. So this one should equal to 0. So this is one is 4 times 4, and this one is 4 times 1. Okay. Right. Of course, the solution of this one will give you determination of this M. This matrix, coefficient matrix, for the boundary conditions, that should equal to 0, right? As we said before, just slightly simplify this one to the 4x4 matrix. Okay. All right. But of course, we know that we consider either symmetric states or anti-symmetric states, and then this one actually will be a lot simpler, because for the symmetric states, we know that this D will be 0, and for the anti-symmetric states, C will be 0, and also A1 and A3, they are related. Okay, so this way, we can simplify this equation a lot. Okay. So we can consider symmetric states. Okay. So in this case, we have A1 equals to A3, and also D2 must be 0, right? Okay. So now the coefficients will be a lot simpler. Okay. So you can see that in the region, you have this one equals to, okay, A1 e to kappa x plus w over 2. And this will be C2 cosine function kx, and this will be A3. But A3 is the same as A1. So now you can simplify this one. This is just okay. So this one be A1. This is A1. This is C2. And this will be also be A1. That's e to kappa x minus w over 2, okay? And this is region 1, this is region 2, this is region 3, okay? And now you can see that, so the wave function is symmetrical. So you only consider the boundary condition at x equals to, for example, minus w over 2, okay? We have only this boundary condition because since you already assume the states is symmetric, so that means the boundary conditions, if the boundary conditions at x equal to minus w over 2 is satisfied, and they will be automatically satisfied at point x equals to plus w. So this one will be equivalent to the boundary conditions at x equals to w over 2. So we just have, now we reduce the boundary conditions equations from 4 to 2, right? So now you have per se minus w, is continuous. Okay, so this immediately leads to A1 equals to C2 times cosine kw over 2, right? So that's one equation. And you also have this derivative. First order derivative should also be continuous. Okay, so this one is continuous. So just do a differential. Okay, so that means kappa A1. Okay, that's a differential on the left hand side. Okay, of in the region 1, and then you take x equals to equal to minus w over 2. Okay, and this one will equals to minus k times C2, and then will be sine function kw plus minus w over 2. So you got this one to be plus, right? So this gives us two equations. Okay, so that means you have a 2 by 2 matrix now. A1 and C2, very simple, right? And this one should equal to 0, and this one will be 1 minus cosine kw over 2, and this will be kappa. There will be minus k sine kw over 2, right? So this is a matrix M. Okay, A1 C2 equal to 0. So this is a 2 by 2 matrix. Okay, and then you see the determination of this one is very simple. Okay, so you look at the determination. Okay, that's equal to 0. This is just extremely simple, right? So this is just immediately got us this one times this one. So this one times this one minus this one times this one should be 0. Okay, so that means so this immediately tells us the equation. That's the cotangent function of kw over 2 equals to k over kappa. Okay, right? And remember, if you use the derivation of this k, remember this k equals to just 2m the energy E over h bar squared, and the kappa equals to 2m, and this V0 minus E over h bar squared, right? So that's the real wave vector in the well and the imaginary wave vector in the barrier. Okay, so you immediately obtain the equation that is the cotangent function Okay, now you have an equation of energy. Okay. Okay. Right. So this is the equation for the symmetric states, right? And then actually for the anti-symmetric states, okay, you should have C2 equal to 0, right? There's only sine function. And then A1 should equal to minus A3, okay? And then the boundary conditions at x equal to minus W/2 actually will lead to a very similar equation. So that is minus the tangent function of k W/2 equals to k over kappa. Okay. Or in terms of energy, that is minus tangent function. Okay. 2. This again is 2m e and w squared over h bar squared. Okay. Equals to e over v minus e. Okay. So the difference, one is a coordinate function, another is a tangent function, right? Okay. And now if you want, you can actually use the to make this equation to be slightly shorter. Okay. So look at this one. So this is 2m times w squared divided by h bar squared. So this is nothing but just the energy of the quantum set in the infrared quantum well. Okay. So remember this, the quantum state in the infrared quantum well with weight w is just the h bar squared and pi squared, 2m w squared, right? So remember this one. Okay. So if we use this one, now we can define the energy as epsilon times E1 infrared, and V0 defined as mu 0 times E1 infrared. That means we use this one as a unit. Okay. So this one is the energy of quantum states in the infrared quantum well, right? So this we just use this energy as the unit. Okay, so that means that's a natural energy scale. Right? So we compare all the energy to this unit energy. Okay, and then these equations, maybe we call this 1 and 2. Okay, so they will become, two simple equations. Okay, one is the cotangent function. Okay, so this is the cotangent function. There's a pi right here, right? And the square root of epsilon over 2. Okay, equals to square root of epsilon over square root of epsilon over mu 0 minus epsilon. Another one is minus the tangent function, and pi times square root of epsilon equals to epsilon v0 minus epsilon. So you can see that these two equations actually are very intriguing, right? Because you know that the tangent function, cotangent function has a very peculiar format. Okay. So now we can, so this is, on the right hand side, they're just the same equation, right? So now you can define one equation equals to square root of epsilon as nu zero minus epsilon. So this function, you can say that this is defined only for epsilon greater than 0 or equal to 0, of course, less than nu zero, right? So this one actually is the upper bound for bounded states, right? So you cannot have energy of the bounded states higher than this barrier, okay? Right, so this gives us one equation like this one. So if we plot this equation, okay, so you can say that suppose this is let me plot this one slightly lower, okay? Okay, so if you plot this equation, okay, so this is 0 as a function of epsilon, or maybe it's better as a function of square root of epsilon. Okay, that's even better, right? Okay, okay, and this is why if we plot this one as a function of square root of epsilon, so when this one is 0, of course it's 0. Okay, so it starts from 0, but then at the frequency say nu zero, this one should be infinite. Okay, so this is this one should infinite. So this one will increase. You know, initially it's almost linearly, but then will go to infinite, right? Okay, so you know that this one will goes to infinite. And now you can define another equation. You know, for the even function, for the symmetric states. You know that you have a cotangent function pi times square root of epsilon over 2 should also equal to y, right? Okay. So what is this function? The cotangent function, you know, goes from infinite. If square root is 0, so this goes from infinite. But then, sorry, that's very bad drawing. Okay, so it goes from infinite. Okay. Right. And then close to 0 at the parallel 2, but that's parallel 2 already right here, okay? So this one actually is for epsilon just equal to 1, right? So this is square root of epsilon equal to 1, okay? So you can say that that one, of course, will give us a solution. So this gives us one solution for the even states. And then similarly, there will be another one. Okay. Right, so give another solution. Okay. And then there will be another solution. That's very bad drawing, sorry. Okay. Anyway, so this gives us one more solution, right? Okay. And you can see that the solution will be something like the solution will be pi over 2 times square root of epsilon equals to m pi over 2 minus the arctangent function of square root of epsilon over nu 0 minus epsilon. And for this, m equals to 1, 3, 5, and so on and so forth. And this is for the symmetric states. And of course, if you look at the antisymmetric states, okay, so the equation is minus tangent function of pi times square root of epsilon over 2 should equal to y. And this one also decays. Now it goes like this one. Okay. It goes from infinite so you know what I mean, right? So this drawing actually is bad. So that gives us one solution. And then another one will be something like this one. Okay, that gives one more solution. Okay. Of course, you have another solution. Okay. So this one will also give us a solution to be pi over 2 times square root of epsilon should equals to m pi over 2 minus the arctangent function of square root of epsilon minus nu 0 minus epsilon. So now you can see that this only for n equals to 2, 4, and so on and so forth. Okay. So now the solution actually can be just given by one equation. Okay. So to summarize, all the eigenvalues can be obtained by pi over 2 times square root of epsilon equals to m pi over 2 minus the arctangent function of square root of epsilon. Okay. Nu 0 minus epsilon. And this is for the n solution. So we put this n index right here. Okay. So you can see that not very simple. And the solutions, of course, you can see that if, for example, if this barrier goes to infinite, and then the solution will be very simple, just equals to n squared, right? That means energy n just equals to n squared times pi squared h bar squared over 2m w squared. That's of course just recover the results we have obtained for the infinite quantum wave, right? Of course, we should obtain this one. And secondly, you can see that if epsilon is much less than nu 0, so you can see that and then the energy will be just this En will be just slightly less than n squared and pi squared h bar squared and 2m and w squared. Okay, and actually quantitatively it is about, so this Em actually is about n squared pi squared and h squared and 2m and w times the coefficients 1 minus 4 over pi square root of nu 0. Okay, so you can see that if this barrier is very high, the energy only slightly below the the energy eigenstates of this one. Okay, and also from this figure, you can see that okay, from this figure you can see that so there is at least one bound state, right? Okay, so you can see that this curve goes from zero. This pink curve goes from zero to infinite. Okay, and then there's at the most at least one eigenstate, which is of course is the quantum state. Okay, and then there's also there's upper bound right here. Okay, so the number of states actually is very simple. So you just count, how many states you can have. You just count at what energy, and this one will be diverge, right? So you can see that as long as this equation has solution, okay, so you can always got an eigenstate. Okay, so the number of states will be simply just given by the maximal. You should have this maximal epsilon m less than Vm, right? So that means actually you should have Vm you should have m times pi over 2, and this one should be, so this means you should have m less than V0, sorry, V0. Okay, so this gives us the number of bound states. Okay, so in other words, this m just equals to the maximal integer number less than this nu zero, which is the barrier in units of the energy of the quantum state. So this basically is equals to V0 times 2m times w squared over pi squared and h bar squared. Right, and you take the maximum value, okay? Maximum integer value below this one. So you can count the number of states, okay? So this way, you can see that if you increase decrease the barrier. So this is suppose this is the barrier. This is quantum well. You have the barrier, okay? So you have the quantum state. So this is the state. This is the energy of the infinite, and then the energy will be slightly below this one. The wave function will be slightly penetrate into the barrier, okay? Because something like this one. And then for the first excited states, okay, will be slightly below the infinite quantum well, okay? And the wave function will be also have this kind of a small penetration into the quantum well, into barrier, okay? And then you have, say, another state right here, which is also below the barrier, okay? And then the state will be also have this kind of penetration into the barrier, right? And the number of bound states will be limited, okay? So this is the maximal m that you can have, okay? So if this V0, okay, is less than the infinite quantum well for the m+1 states, and this will be the m, right? So that means it's very easy to count the number of bound states in this quantum well, okay? just using this solution. Okay, right. So this gives us a kind of example of finding out the eigenstates. Okay, of course, in this case we have a good symmetry to use. We have the good approximation to use. Okay, and also we have this diagram solution. Anyway, it's a very simple example. It has only 3 regions and it's symmetrical. So we have a 2x2 boundary condition matrix to be singular. Okay, so it's quite easy to obtain the solution. Okay. All right. And but in general case, of course, you need to use numerical method to find the eigenvalues. Okay, to satisfy that boundary condition, basically determination of the matrix of 2i plus 2 times 12 plus 2 matrix to be singular. Okay. All right. So this is for the 1D boundary states. Let's say if you guys have more questions, okay, feel free to ask. Okay, so let's come back. Now I will give you another example, but this time I will not solve it fully. Okay, I will try to just outline the main steps, and then I leave the calculation to you. Okay, as an exercise, or you can just follow the steps in the lecture notes. But we try to expand the physics. Okay, more. Okay. So let's consider the double quantum well. So the potential is like this one. Okay. But let's consider even simpler case. Okay. Let's consider even simpler case. Consider quantum well that's infinite. But now we have a barrier inside this one. Okay. So this goes to infinite. Okay. And this one v equal to 0. V equal to 0. And this one v just equal to v0 is a constant. Let me put this one to be symmetric. So this is x, so we put this one to be minus a, this to be a. This is w plus a. This is minus w plus a. Minus a. Okay. So it's a symmetrical potential, right? It's a quantum well. You know that this one must be a standing wave, right? For example, the ground state. Okay, so let's consider case, a simple case. So what if v0 goes to infinite? If v0 goes to infinite, actually, you have an even simpler case, right? You have just basically 2 quantum well. Okay. So it's a solid wall, separate 2 infinite quantum well. Okay. And then the solution for each of this one actually is solved. Right? So the first one is just a standing wave like this one. The second one is just a standing wave like this one. And it's the same for the second quantum well. Okay. So basically, you can say that you have 4 states. You can call this one percent 0, but on the left. This is percent 0 on the right. This is percent 1. Sorry, this is percent 1. Percent 1. This is percent 2 on the left. This is percent 2 on the right. Okay. And the energy of E2 on the left, of course, equals to energy if the particle is on the right quantum well. On the right, right? And the E1 on the left so equals to E2 on the right. The both equals to, this case equals to pi squared, h bar squared 2m W squared. And this one equals to 4 pi squared, h bar squared, 2m W squared, right? So on and so forth for the higher states. In this case, we say that we have twofold degeneracy. Okay, so the particle, for each energy, there are two states, two possible states. One state is that the wave function is finite only on the left corner valve. And then another case is that the wave function is finite on the right corner valve, but they have the same form, okay? So you have kind of states like this one. But this one, of course, is only true when this one is infinite. But if this one is not infinite, we know that wave function can turn into this corner valve, okay? So if it's not it's not infinite, if it's finite, okay, you know that so you have a state right here, right? So originally you have a state like here, and you have the same state right here, okay? So the wave function should be something like this one. But now, because you know that if you have the barrier to be finite, and this wave function should go, let's put like this one, should go still go 0, but now has some probability enter into this one. Okay, and the same for the right corner valve. Okay, and suppose this is energy, and this one is an even states. So this is a new ground state, percent 1. So the energy will be slightly below this one. Why? Because you can say that the standing wave starting from here, okay? The standing wave from here, and this supposedly this wave vector is slightly smaller, right? So you have this wave vector, this is k prime. So k prime 1 should be less than k1, the original one. So that means the energy, this new energy should be less than E1L. That equals to E1R, right? Okay, because the wave function has some probability to penetrate into this barrier. So it means the wave vector within the corner valve will be slightly smaller. So the energy will be slightly lower, okay? So this is the state for the ground state. It must be an even function. It must have no nodes, okay? And then there will be another state. That will be slightly higher than this, okay? The energy will be slightly higher. So now in this case, now you still have a bounded states like this one, but now this one now is anti-symmetrical. Okay, goes like this one. So this will be percent 1x, percent 2x. Okay, and this percent 2x will be anti-symmetrical. Okay, so you have this energy will be slightly above this one. Okay, and of course you can go for the higher states. The solution again is still you can write in this different regions. You call this one region to find the solution of this. You find this one is region 1. This is region 2. This is region 3. Okay, so the wave function can be written as on the left hand side. So it must be kind of functions that is a standing wave at x equals to w minus a, right? Let me see the notations, okay? Right. So let's consider symmetrical states first. Okay. And for symmetrical states, you you must have this one, so it can be written as a times a sine function. There's a v vector k, right? And then x plus w plus a. So this way, you make sure this one is a standing wave. It satisfies this boundary condition at x equals to this one. This is in the region 1. And the region 2 is a symmetric function. So it must be written as b. And then you have e to kappa x plus e to minus kappa x. Divided by 2. That's a cosine function, right? This is for the region 2, okay? And then for the region 3, because it's symmetrical, so it should also be divided into a. That would be a sine function k, let's say x minus w plus a. Let me see if you change it. So this is minus a. This one should be minus or plus. Let me see. If you want this one to be symmetric, wave function, you're going to find the states to be if percent x equals to percent. So this should be a minus sign, right? So if we change x to be minus x, oh, sorry, this should be plus sign. So if you would have x equals to 10, right? So this way, I want to make sure this is correct. Yeah, I think it's a minus, okay. Right, so this is for symmetrical states, okay? And then you have boundary conditions. So you have percent x and d percent dx. They both are continuous at x equals to, this is minus a, this is plus a, minus a, right? And of course you have another one at plus a. And you can obtain this, you're going to have two equations, okay? For two coefficients, a and b, okay? So that means, again, you need to find the, determination of this matrix to be singular, okay? And similarly, for the anti-symmetric state, okay? Right. So you can, this way you can find the eigenstates, and also you can do the same thing as we have done, for this large barrier approximation, okay? So I will not go into the details, but the results will be actually confirmed of this combination. So you're going to have two states, as the ground states and the first excited states. Let me draw this one again, like this one. So if you have a high barrier, okay. Suppose you have, if we have the original barrier is infinite, we know that there will be two states right here, right? One is right here, another is right here. So we call this one, say, this is E1R, this is E1L. But now you can form two states. One is the even states. That's states has energy slightly below this one, and the wave function actually will be a symmetrical wave function like this. Okay, so this is E1. Let's say this, and the wave function is cosine 1 x. And there will be another state. Let me try to exaggerate a little bit this energy, okay? That's slightly higher, okay? And this energy will be something like this one. So the wave function will be, actually will be antisymmetric. Okay? So this is, sorry, E2 and cosine 2x. And actually, they're almost like a symmetrical and anti-symmetrical. If this V0, if this V0 is much greater than E1 and E2, okay? So you're going to have this wave function cosine x quantum set is almost like the symmetric. It's almost like symmetric combination. And cosine 2, it's almost like a anti-symmetric combination. Okay, of course, this is approximation. Okay, right. And this states the energy, of course, you have E1 is less than E2. Okay, so you can have the origin you have two states which are degenerate. Okay, E1R equals to E1L. So this is a degeneracy, right? So you have two degenerate states, but if you have a barrier, this will be split into two states. Okay, so you have one state, two states, and they're going to split into E2 and E1. Okay, and this splitting, we call this one the bonding energy. So this state is called has a name called the anti-bond state. This one is the bonding state. This is anti-bonding. So why do we call this one? So we are actually using language of molecular. Suppose you have two atoms. So this is one atom, this is another atom. And the electron can be in one atom or can be in another atom. But if we put two molecules close to each other, and actually this electron can be simultaneously on the left atom, on the right atom. And if they form a symmetrical states, the energy will be lower, right? So what that means the energy be lower, that means they're going to release a little bit of energy. Or in other words, if you want to have the wave function to be more separated than them. So in the anti-bonding states, you need to excite the atom, the electron from the low energy states to high energy states. That costs energy. This one is called so this is going to be called as the bonding energy. Right. So that means to make this electron to be more shared by the two atoms to a less shared states, more isolated states, you need to input some energy into the system. That costs energy. So this means the lower state will be more stable. And in this case, the electrons has more probability in the middle of between the two atoms. Okay, so it's like a glue, right? To bond these two atoms to form a molecule. Okay, so this actually is the bonding state of this molecule. So this is one thing. Okay, right? So that's the bond states and anti-bond states. Let me say, is that, oh yes, there's a typo. Thank you. So it should be minus that. Thank you. Yeah. So this way, using this model, you can kind of understand the formation of bonding and anti-bonding states, and why the two atoms can be bound together, because the electron can be in simultaneous on the left and right quantum well to form a symmetric states. Okay. Right. So this is one result. Another thing is that what if you put the electron initially left the quantum well? Okay. So what if psi x equals to psi 1 Lx, okay, at t equals 0, right? So that means okay, so you put a wave function, it's something like this one. So what will happen? I know that this state is not eigenstate, right? So this one is not eigenstate. So, but then you have psi 1 Lx approximately can be written as the square root of the ground state and plus psi 2 x. Okay, so that means the evolution over time now can be written as approximately psi 1 x e to minus I e1 t over 2 over h bar, sorry, plus psi 2x e to minus I e2 t over h bar. Okay, and this one can be written as of course square root of 2 psi 1 x plus psi 2 x e to minus I e2 minus e1 divided by h bar and then times t. And there's a common phase factor, which this is a global phase factor, not really important, okay, times this one. And now you can see that at t equals 0, right? So this one is giving you this one. But say what if as t equals to pi times h bar divided by e2 minus e1. So what will be this time? At this case, you can say that psi x t actually is going to be approximately square root of 2 psi 1x minus psi 2x times a common phase factor, right? Which actually is not really important. But look at this one. This one is just approximate to the quantum well state on the right side. Okay, so that means this one you can have a state to be something like this one. So this is t equals to pi times h bar over e2 minus e1. Okay, this one is at t equals 0, right? Actually, in the half time of this one, so you can have a superposition of this. So you can also consider case, right? You can consider other cases. For example, what if t equals to pi times h bar over 2 divided by e2 minus e1. So you put this in this one, you're going to have psi x is going to be, let me just throw away those global phase factors. So that will be psi 1 x plus psi 2 x, and then times e2 minus I pi over 2, right? So in this case, you actually have a kind of a superposition of the psi 1 x and psi 2x, but that's an imaginary number. So interference will make this probability, to be equally in the left corner well and the right corner well. Okay. So now you can plot px, okay, at a different time. At t equals 0, you know that it's going to something like this one. Okay, so this is a quantum well. Okay. And then at t equals to pi over 2 times h bar over E2 minus E1. Okay. So you're going to have a superposition of this. Okay. So now you have the probability will be something like this one. Right. And the phase of this one, this is going to be 1 plus I. This is going to be 1 minus I. Okay. Right. And then if I have t equals to pi times h bar over E2 minus E1, that's the case we have for consider here, right? And then the wave function will be on the right-hand side of this quantum well. And the probability will be just something like this one. Okay. And similarly, you have t equals to pi times 3, times h bar over 2 divided by E2 minus E1. And then this one will be again. Okay. After the probability like this one. And the phase, of course, will be, this one will be 1 minus I, this one will be 1 plus I. Okay. So basically, in a period of 2 pi of times h bar over E2 minus E1, and this particle will oscillate between the left and the right quantum well, right? And this, so there's a tunneling through this barrier. Okay, and the period t just equals to 2 pi times h bar over E2 minus E1. Okay, right. So you can say that the angular frequency is just omega equals to E2 minus E1 divided by h bar, right? So you can see that if you have this kind of a double quantum well and separated by a high barrier and place the particle on the left quantum well, actually you can turn it from the left to the right. So this is particularly true for quantum mechanics, right? So if you have a classical mechanics, actually you won't have this one because the particle, if it's confined on the left quantum, it has not enough energy to jump over this barrier, okay? Right, so this is something, only true for quantum mechanics. It's not possible for classical. So in classical mechanics, if you place the particle on the left, it will always stay on the left if it does not have enough energy to jump over this barrier. Right? But in quantum mechanics, it can oscillate between the left and right quantum well, right? Even though the energy is below the barrier, of the wall. Okay, so that is the case of this double quantum well. So we just try to present this physics without doing much mathematics. Okay, and so the mathematics actually can be followed follow the same procedures as we have done for the single quantum well. It's slightly complicated by still for 2x2 is a solution of 2x2 measures. Okay. All right. So any questions at this point? Okay. So if there's no question, so now I want to introduce a little bit advanced materials. I want to say that how can we transfer the Schrodinger equation to Heisenberg matrix form, quantum mechanics. Okay, so in this case, we translate this Hamiltonian, that's the operator, right, in quantum mechanics, in Schrodinger equation, into a matrix. Okay, into matrix H. And then this Schrodinger equation, time-independent Schrodinger equation, right? Find this eigenvalue actually will become a matrix equation. But this percent now is a vector with coefficients that equals to E and percent. So this is the eigenvalue of a matrix. Okay. How can we translate into this one? So the idea is that let's consider the bounded state of potential like this Vx. Okay. And now we cut this into many small pieces, as small as you can. Okay. So that each of this one has a distance to be delta. Okay. Right. And then you can approximate this potential as steps. You can just take this as constants, say like this one. Okay. Right. So basically, you are discrete this. So you make this into small steps. So make the potential to be something like to PHYS. Right, so on and so forth. And also, so we call this one Vi. And similarly, the wave function, we take the wave function also, approximately as piecewise constant. We call this one percent I. Okay. And then we have a differential, right? So we have a differential percent x. Okay, that's d percent over dx. And now you take this discrete value, so you can say this one to be, say, percent I plus 1 minus percent I divided by delta, right? So this is, of course, just like you do numerical calculation. Okay, you can take this discrete value. And then a second order derivative now can be written as the percent I plus 1, minus 2% I minus plus pi I minus 1 divided by delta squared. Okay, so this is a way to write down this differential, this second order differential operator into the discrete form. Okay, right. And now we look at this time-independent Schrodinger equation. This is TISC. So that is a minus h bar squared 2m d squared over dx squared and percent and plus vx and percent x. So this is equal to e vx, right? So you take this one at the ice point, you can see that this is going to be minus h bar squared, sorry, over 2m. And then this will be 2% I plus 1 minus 2% I plus percent I minus 1 divided by delta square. Right, so that is the discretization of this second order derivative. And then plus percent I times percent I. That will equals to E times percent I, right? Okay. That's okay. And for example, you can take the equation. Okay. Let me just, this is a little bit long. Let me define tau as h bar squared over 2m delta squared, okay? So that we can have this one to be slightly more compact, okay? And then you can see, for example, you can have an equation to be minus tau okay, so the minus tau, say for example, you have percent 3 minus 2% 2 plus percent 1, okay? And then plus V2 percent 2, that equals to E percent 2. And similarly for the next one, that's a percent 4 minus 2 percent 3 plus percent 2 plus V3 percent 3 equals to E percent 3, right? And so on and so forth. You can have percent, say M minus 2% M minus 1 plus percent M minus 2 plus V M minus 1 percent M minus 1 equals to E times percent M minus 1, right? So you can continue this one, to the left and to the right. But let's assume that the wave function is bounded, right? So at a certain point, the function can be, approximately taken as 0. So let's say we have the boundary condition. We have the boundary condition percent at 0 equal to 0, and the percent M plus 1 equal to 0. Okay, so that means on the left, on the right. So if this region take big enough, you can always take this wave function to be 0 because it's a bounded state. And then you have the state on the side 1 will be minus tau. Now percent 1, percent 2 minus 2% 1. Now it's going to be plus 0, right? And plus V1 percent 1 equals to E percent 1. On the right, you can also have this one. That's minus. Now percent M plus 1 is 0. So minus 2% M and plus percent M minus 1. And plus Vm percent M equals to E percent M. Okay, so now this is the equations. How many equations do we have? 1, 2, 3, so on and so forth. So there are percent M. So there are n equations. How many coefficients do we need to calculate? For the wave function, we have percent 1, percent 2, percent M. Okay, so there are n coefficients, right? So now we can define a matrix. Okay, for this one we have the coefficients. So it's going to be, V1 plus 2 tau, and then is minus tau, and then 0, 0, right? So on and so forth, and 0. And then for the second equation, you have this is going to be minus tau. This is a V2 plus 2 tau, and then minus tau, and 0, and so on and forth, and 0, right? And then for the third equation, that's 0. This is a minus tau, and the V3 minus plus 2 tau, and there will be tau, and minus tau, and so on and so forth, and there will be 0, right? So you can continue this one. For the M minus 1 equation, okay? So this will be minus tau. This will be Vm minus 1 plus 2 tau. There will be minus tau. Okay, and this will be 0. Okay, and then you have a 0. Okay, and 0, 0. This will be Vm. Sorry, minus tau. Okay. This will be minus tau. This will be Vm plus 2 tau. And this will be minus tau. Vm minus 1 plus 2 tau and minus tau. Okay. So you can see that you're going to have okay. Right. So this is the matrix. So you can see that this is a m times m matrix. Actually, it's symmetric. Okay. So that means this H, if you take the transpose, just equal to itself. And also, it's real. Okay. So this means this matrix actually is also like this one. So you combine these two. We say that this matrix is a Hermitian. So that means you take the deck, that is Hermitian conjugate, which is you take the transpose first, and then take the complex conjugate. That's itself. Okay, right? So with this definition, so you can also define this wave function, defined as the vector that's percent 1, percent 2, and percent m minus 1, percent m. Right? You can use this set of coefficients to specify the wave function, right? And then you have now the Schrödinger equation after discretization. Okay, after discretization, you have this matrix, we call the matrix of the Hamiltonian, acting on this vector, which just equals to E percent vector. Okay, right? So this is the equation that we have. So this is n times m matrix. This one is n times 1, the column vector. Okay, and this one is the eigenvalue of this matrix. Right. So the independent Schrödinger equation becomes of the eigenvalue problem of a matrix. Okay. But linear algebra, you know that this matrix is a Hermitian. Okay. So that means all the eigenvalues be real numbers. Right? And the solution are just determination of this right. So basically you needed to find out the eigenvalues of this matrix. Okay, and then you solve the problem. So this one can be done numerically. Right. So this not only give us formalism, a new formalism of quantum mechanics, but also give us a new way to calculate the eigenvalues and the eigenstates of this potential. Okay. Right. So that is the the Hamiltonian. But actually, if you look back at this one, so you can see that this one has two terms. One is this V, right? So this one is diagonal. You have another term that comes from this tau, okay? So we can actually separate these two. So if you want to, you can write down this one into two parts. You can define this V matrix as very simple, just V1, V2, and then Vn, and this is 0. Okay. You define another matrix K that only contains this tau. So that is 2 tau minus tau, 2 tau minus tau minus tau minus tau, 2 tau minus tau. Okay, and so on and so forth. And then you have minus tau, 2 tau minus tau. Okay, and then you have minus tau, 2 tau, and this is 0, and then this 0, 0, 0. Okay. Right. So you can define this one as another measure. This one equals to h bar squared times 2m delta squared. Okay. So you can see that this one, of course, comes from the potential. Okay. We call this one potential matrix. And this one comes from the kinetic energy. We can call them kinetic matrix. Okay. So actually, the Hamiltonian matrix is just a summation of this kinetic energy matrix plus this potential energy matrix. Okay. So in general, any operator can be written into a matrix. Okay. So this way, we realize the time-dependent Schrodinger equation, okay, becomes a matrix form. Okay. So that is Heisenberg's formalism. Okay. Okay. So you can see that actually we can also consider a state. Okay. The operator becomes a matrix. N times n matrix. Okay, it's a square matrix, and the state becomes a vector or a column, right? Matrix is n times 1 matrix. Okay, right? This is n times n matrix. Okay, so we have this kind of a translation. Okay, so that gives us a way to derive the matrix form of quantum mechanics using the Schrodinger equation, right? So in this case, we are trying to discretize the real space wave function. Okay, but later on we also learn even more general cases. So we can use eigenstates, to expand the wave function, and then we can actually translate operators in Schrodinger equations into matrix, in other bases. Okay, but this is the first flavor of how we can derive this matrix formalism of quantum mechanics. Okay. All right. So this is pretty much what we have for today. Okay. So this part, this matrix form part, okay, is optional materials. So it will not be tested in mid-term examination or the final examination. Okay, so this is optional, just for your fun. Okay. All right, so we're going to stop right here. See if you have questions. Yes, double quantum error is also optional. Okay, so it's not going to be covered in the examinations or homework problems. Okay, so but you are encouraged to read the lecture notes so that you can get a more feeling of this kind of one-dimensional bounded states. Okay. Yeah, this part is also optional. So what is the use of matrix form? That's a good question. First of all, this gives us a way to find a solution in the computer. Right? In the computer, you know that you have a digitized memory. You cannot store a function that's continuous. Okay. So then we have to approximate a continuous function as discretized, matrix. Right. So we just find out the values of these functions at several sets of points. Okay. And then you can use the computer to do the calculation. Okay. So that's one way of this one. Another way, more fundamentally, so it will give us more convenient mathematical tools to understand the structures of the states and the eigenvalues. Okay. For example, it's not that obvious from the Schrödinger equation that all the eigenvalues must be real numbers, right? So it's not that straightforward. Of course, if you are familiar with the partial differential equation theories, you can know that for this partial differential equations that have right boundary conditions, you must have the eigenstates and eigenvalues to be real numbers. But if I translate this one into a matrix, and then it will be immediately, it's obvious for you, right, to know that all these eigenvalues must be real numbers, right? Okay, so there's a question about how to combine the even states and ordered states into one equation, find the quantum well. Okay, let me. This one needs a little bit more writing. So one equation is like a cotangent function, pi times square root of epsilon over 2 equals to this square root of epsilon nu 0 minus epsilon, right? So you know that for this equation, and you do the arctangent function, okay? So this one can be written as pi over 2 square root of epsilon and m pi over 2 minus the arctangent function for m equal to 1, 3. Okay, so why? So actually you can write down this cotangent function. You know that any cotangent function x can be written as a tangent function pi over 2 minus x, right? Okay, so that means you can write down this cotangent function pi over 2 epsilon, right, as a tangent function of pi over 2 minus pi over 2 times square root of epsilon. And this one equals to this. Right. But of course, this also equals to tangent function of m pi plus pi over 2 minus pi over 2 times square root of epsilon, right? Equals to this one. Okay, because tangent function is periodical with a period of pi, right? So not from this one, or you can put this to be minus, it doesn't really matter, right? So immediately you obtain that, plus Imagine now obtain this one. So m pi plus pi over 2 minus pi over 2 square root of epsilon equals to the arctangent function. Okay. Now this one is the same for this. Okay. And then you can write down this one as pi over 2 square root of epsilon just equals to 2m plus 1 times pi, right? Minus arctangent function of okay, right? So that's the same as this one, right? But now you take this n equals to 1, 3, and similarly, this is for the even functions, right? Even eigenfunctions. Okay, for the order states, okay, and that the boundary condition equal to 0 give us minus the tangent function pi over 2 times square root of epsilon equals to this one. That's even easier, right? Sorry. So this means the tangent function, pi over 2 times square root of epsilon equals to minus this one. Okay. You take the arctangent function, and you know that this is a periodic function, so you have right. And then you know that if you write this into over 2, this will be 2m, right? So that's why. So you can see that if you compare this one and this one, they're actually of the same formalism. The only thing is that for the even eigenfunctions, this n will take values to be 1, 3, and so on and so forth. Okay. So you can take this one to be m. So with n equals to 2, 4, 6, and so on and so forth. Okay. Right. So that's why. So let's say any further questions? So why n less than new 0? Okay. Great. First of all, the solutions, all the solutions, okay, is given by right. So you can say that all this epsilon must be less than u0, right? Otherwise, this arctangent function, you're going to have imaginary, okay, right? To make this one is a positive number, right? Okay. Otherwise, you wouldn't have this one. And secondly, so you can see that if you take m, it's greater than or equal to new 0. So you can see that this this function, because this one is always less than any arctangent function of x is always less than pi over 2, greater than minus pi over 2, right? So that's the definition of arctangent function. This is x. This is arctangent x. Always goes like this one. Okay. So for this one, you can find that you can have epsilon is going to be greater than, okay? If n is greater than that one, you find that you're going to have, so you must have, sorry, you must have, let me say, you put this back into this one, let's say, m pi. We have arctangent function of this epsilon and the new zero minus epsilon, and this one equals to pi over 2 square root of epsilon minus m, right? You have this one less than pi over 2, greater than minus pi over 2. Okay, right? So you can see that this m will be bounded, right? So you can see the value of m is going to be bounded because this square root of epsilon is at the most new zero. So m must be less than this one by 1. Okay, right? Okay. So otherwise, you will not have a solution of this one. Okay. Of course, we have already used the n is an integer number. So could you explain again how to get the approximation of ×1 and ×2 in double quantum well? When okay, so we have actually didn't get this one for so that requires a little bit of calculation. Okay. I don't have a short answer for this. Okay, but let me say. So the question is, if E0 is much greater than E1, E2 in double quantum well, okay? Why this ×1 approximately equals to square root of say ×1L plus ×2L R, and ×2 is about ×1L minus ×2R, right? So basically, so for the real calculation, you need to go into the details of the notes, okay? But let me just write a little bit like this one, okay? Suppose this one is a very high barrier, and you know that the eigenstates can be written like this one, right? So you can see that this wave function on this one should be a sine k x plus w plus a, something like this one, right? Percent equal to something like this, okay? It should be symmetrical. So in the middle, it should be something like a C and E kappa x plus E2 minus kappa x over 2, okay? And then another one will be, say, should be A sine K x minus W minus A, and there's a minus sign, okay? This is for the even states, right? Similarly for the, and you can see that if this one is goes to infinite, okay, and C should go to 0, right? Because you can have very small probability for this wave function entering into this barrier, okay? So in this case, K goes to almost like a, if this will go to 0, you know that this is almost like a standing wave, right? And A sine K x plus W plus A is going to be a standing wave. So that means K goes to nothing but as pi times h bar over W, right? So then this function goes to almost like a ×1 Lx. Right. So then with this, so percent 1x is almost like a percent 1L. And now this one is going to be the symmetrical form. So percent 2R, right? So percent 1R. Okay. It's symmetrical, right? And similarly, you have a percent 2x, that will be percent 1L minus percent 2, percent 1R, okay? Because it's anti-symmetrical. So if you have a very high barrier, so this is C. It's going to be very small, okay? So if C is very small, and this wave function on the left polymer is almost like a standing wave, right? And then this K must be very close to H bar over W times pi, right? So that is the explanation. And of course, if you want to do that, you have to do some calculation, okay? Yeah, all the things we talk right here have been covered in the lecture notes, okay? So the lecture notes is very detailed. We don't have time to cover everything in lecture notes in the lectures actually. I have put quite something in the lectures, so it's impossible that to use so limited time to cover every contents in the lecture notes. And in the lectures there are also a few more examples, and there are also some exercises. Some of them actually quite interesting. So you are really encouraged to do some exercise in the lecture notes. Okay.